Welcome back to G Fun Facts Online. Today we are diving deep into one of the most mind-bending intersections in modern science. We are going to explore how the tangled web of neurons in your brain and the sprawling infrastructure of the internet might actually be governed by the same exotic mathematics that describe black holes in the fabric of the universe itself. We are talking about the collision of complex network science and string theory. For the better part of a century, the way we understand networks has been dominated by something called graph theory. If you have ever seen a map of the London Underground or a diagram of your Facebook friends, you have seen a graph. It is a collection of dots, which we call nodes, connected by lines, which we call edges. This abstract view is incredibly powerful. It gave us the concept of 6 degrees of separation and the small world effect. It explains why you can get from a Wikipedia page about toasters to a page about Genghis Khan in just a few clicks. But there is a problem. Traditional graph theory treats these connections as simple, dimensionless lines. It assumes that the link between two neurons, or the fiber optic cable between two cities, is just a logical connection. But in reality, networks exist in physical space. Neurons have thickness, volume, and surface area. They have to navigate the crowded environment of your skull without passing through each other. The internet is not just a cloud of ideas. It is buried copper and glass that has to respect the curvature of the Earth and the cost of materials. When scientists tried to predict how real biological and technological networks grow using simple graph theory, their models hit a wall. Real brains and real root systems looked inefficient by those standards. They were winding and twisted. The missing ingredient was geometry. But not the flat Euclidean geometry we learned in high school. It turns out that complex networks exist in a twisted, non-Euclidean reality that closely resembles the bulk space described in string theory. This brings us to the first major pillar of this new field known as network physics, and that is the discovery of hyperbolic geometry. In the early 2000s, network scientists noticed something strange. If you try to draw a map of the internet on a flat piece of paper, it looks like a mess, a hairball. But if you map it onto a hyperbolic space, which is a space of negative curvature, shaped like a saddle or a Pringle chip, the chaos suddenly untangles. In hyperbolic space, the area expands exponentially as you move away from the center. This perfectly matches the structure of the internet and branching trees. You have a small core of backbone routers at the center, and as you move outward, the space expands rapidly to accommodate billions of user devices at the edge. This was a massive revelation because hyperbolic geometry is the native language of general relativity and string theory. Specifically, it is the geometry of anti-de Sitter space, or ADIS space, which is the theoretical playground where physicists study quantum gravity. Suddenly, network scientists realized they were looking at the same math as the string theorists. This connection goes deeper than just the shape of the map. It changes how we understand the links themselves. In classical graph theory, a connection is a one-dimensional line, but string theory posits that the fundamental constituents of the universe are not points, but one-dimensional vibrating strings. When researchers at Northeastern University applied this stringy view to the brain, they stopped treating axons as lines and started treating them as three-dimensional tubes or closed strings. These tubes have surface area and volume. They require metabolic energy to maintain their membrane tension. When you model neurons this way, you find that they do not minimize the total length of the wire. Instead, they minimize their surface area and bending energy. This is mathematically identical to the Nambu-Goto action in physics, which dictates how strings and brains move through space-time. When researchers applied this action to the neural map of a mouse brain, the predictions matched the biological reality with uncanny precision. The brain is not wired like a computer chip. It is wired like a vibrating system of interacting strings. But the most profound connection lies in the holographic principle. In theoretical physics, the AD-SCFT correspondence states that a theory of gravity in a complex high-dimensional space, which we call the bulk, is mathematically equivalent to a quantum field theory living on the flat surface of that space, known as the boundary. This is the idea that the universe is a hologram. Network physicists have begun to treat complex social and biological systems as holograms. Imagine your social network as the boundary. That is the observable data, the specific likes and connections you can see. But beneath that, there is a hidden, latent geometry, the bulk. This hidden space represents the invisible social hierarchy, or the thematic distance between ideas. Just as gravity in the bulk dictates the motion of particles, the gravity of this hidden hyperbolic space dictates who becomes friends with whom. If two people are close in this hidden geometric space, they are highly likely to connect in the real world. This is not just a metaphor. The math of the Ryu-Takayanagi formula, which calculates entanglement entropy in quantum systems using geometry, has been successfully adapted to measure information flow in social networks. The entanglement between two communities is proportional to the size of the minimal surface cutting through that hidden geometric space. This leads us to the concept of the brain as a tensor network, Physicists are now modeling the brain using structures called MIRA, or multi-scale entanglement renormalization ansatz. These are mathematical structures used to describe quantum states, and they look exactly like a discretization of hyperbolic space. This suggests that the brain performs a process called renormalization. It takes millions of noisy sensory inputs at the microscopic layer and compresses them into higher-level concepts. It builds an extra dimension of meaning out of the flat inputs of the senses. This implies that intelligence itself might be a holographic projection. The geometry of thought is hyperbolic, branching out from general concepts to specific details, exactly as predicted by the geometry of ADS space. We even see this in the Internet's routing. The Internet has crystallized into a hyperbolic structure to solve a massive problem. If the web were a flat grid, you would need a global map to find a path from A to B, which is impossible to maintain for billions of devices. But in a hyperbolic network, you can use greedy routing. A packet of data simply moves to the neighbor that is geometrically closer to the destination in that hidden latent space. Researchers have shown that this works with near 100% efficiency. The engineers who built the Internet unknowingly obeyed the laws of Einstein's field equations. They built a network that minimizes transport cost in a curved geometry, effectively creating a gravity that pulls data packets toward the core hubs before flinging them out to their destination. This brings us to the concept of the network landscape. Just as string theory describes a landscape of possible universes, network physics proposes a landscape of possible networks. Every possible brain or power grid is a point in this landscape. The elevation represents the energy cost. Evolution pushes biological systems into the valleys, the stable, efficient configurations. We are using tools like flux compactification to understand why nature picks certain architectures over others. Why do all river deltas look the same? Why are there no square brains? It is because these structures correspond to the ground states of the string theory equations applied to network growth. Finally, this convergence points toward a future of quantum networks. Many physicists now believe that spacetime itself emerges from the entanglement of quantum bits, a concept known as EID, from qubit. If space is just a network of entangled qubits, then network physics is not just an analogy for reality, it is reality. We are approaching a point where the study of the Internet and the study of the fabric of the cosmos are mathematically indistinguishable. Both are information processing systems that optimize geometry to move bits efficiently. This knowledge is already being used to design better AI architectures that learn faster using hyperbolic geometry, and to build infrastructure that is topologically protected against failure. We are witnessing a paradigm shift. By donning the spectacles of string theory, we reveal that the complex networks of our world are elegant, geometric structures vibrating with information, shaped by the same fundamental laws that sculpt black holes. The branching of a neuron, the routing of a tweet, and the curvature of the cosmos are all verses in the same mathematical poem. Thank you for listening to this deep dive on Fun Facts Online.